Alright guys, I'm going to start this video. This is an interesting illustration of what if you could ride or travel at the speed of light. So you can see we are leaving the surface of the sun and we're traveling outward away from the sun at a speed of 186,000 miles per second, which is obviously really fast. By the way, in miles per hour, that's 670 million miles per hour. It's super fast, right? But at this speed, when you're traveling great distances, it's actually kind of slow when you really think about it. Now, if you look at the information that's listed in here, and I'll put this video on the agenda for today, but so you can watch the whole thing. It's pretty long. It's like a 45-minute video. And why is it so long? Because it takes a long time to get to planets traveling at the speed of light, because they're so far away. So Mercury is not going to appear in our video for another 2 minutes and 6 seconds, as you can see in the top right corner. So far, we've been traveling for a minute, and we've gone 22 million kilometers. So obviously, we're traveling really far distances in a short amount of time, but when you're talking about really, really massive distances to get to different places in the solar system and even in the universe, the speed of light is actually kind of slow. Even if you could travel at the speed of light, it would take a long time to get places. So when the light leaves the sun, it takes about 8 minutes for it to get to the Earth. So when you're looking at the sun in the sky, it's actually 8 minutes old, right? Which is kind of fascinating. In order to travel to the nearest star, light from that star is going to go through a vacuum, through outer space, and travel for a very long period of time. In fact, it travels for 4.5 years before it actually reaches our eyes, which is kind of crazy. Those photons going through outer space and finally getting to your eyes 4.5 years later. It's kind of crazy when you think about it. That's the nearest star, by the way. It's 4.5 light years away, which means it's been traveling for 4.5 years. Kind of crazy, right? So the stars that are out beyond our solar system, and even the ones that are in other galaxies, the light's been traveling from those galaxies for years and years and years, millions of years in some cases, and finally it reaches us. So the whole thing is really kind of fascinating when you think about it, that even though light speed is really, really fast, when you're talking about really big distances, it really isn't that fast, okay? So we're coming up on Mercury. I've been talking for the last 3 minutes, and you can see we're coming up on Mercury in 18 seconds, T minus 15. And what I'd like you to see, I'm gonna fast forward after this, but watch how fast we go by Mercury. It's gonna appear in your screen, and it's gonna disappear pretty quickly. So when you're traveling light speed, it's a blink of an eye. Watch, there it goes. Okay, so pretty cool. Venus won't pop up into our video for another 3 minutes, or 2 minutes and 40 seconds. If I fast forward through this video and I get to about here, okay, I'm at the 7-minute mark. Now we're going to reach Earth at about another 50 seconds or so, so we can fast forward a little bit more. 10 seconds, 9, 8, 7, 6, 5, 4, and watch how fast Earth goes by, and the moon too. There's the orbit of the moon, there's the Earth, there goes the moon. Okay, so just to kind of show you how fast light speed is, but how not fast light speed is too. Anyway, so I'll stop it there, and we'll just talk briefly about some of the planets, and then I'm going to give you some questions today. All right, so we're just going to take a quick tour of the solar system, and I just want to start with the idea of heliocentric and geocentric. You guys need to know the difference between the two of them. I know you learned about this in social studies already, and I mentioned it in another video about Kepler's laws, but the idea of geocentric model was held before the 1600s. Everybody thought everything went around the Earth, which, it's kind of a logical understanding of everything, because you see stuff go across the sky, so you think it's going around you. But obviously, with more observations of the solar system, we discovered, and a bunch of other scientists back in the early 1600s discovered that everything was actually going around the sun, which is called the heliocentric model of the solar system. Helio meaning sun, and centric meaning centered. Okay, so Copernicus was the first guy to develop this. It was later upheld by Galileo. Galileo was actually put under house arrest because of his beliefs of this. Kepler, which we already talked about, kind of solidified the idea. And since then, it's been obviously the theory that's held up to observation. So those are the two models of the solar system. You got to know them, and obviously the heliocentric model is the true model. Now, one other thing that I wanted to mention, and there's a lot of theories as to how the solar system came together. There's a video that I put out the other day about how everything's kind of in the same plane. They think that the solar system was a bunch of gases that then condensed around the sun, and all these gases, as they were coming together, were kind of condensing and colliding with each other and making larger bodies that then turned into planets. Most of the things that consolidated were about the size of maybe a softball size, but others kind of grew larger and larger. As they did so, the heavier elements would sink to the bottom, right? Which makes sense. You know, if you put something that's more dense, it's going to sink to the center. And so, as the gravitational pull became stronger because of their mass, the denser elements would sink right to the center. So this is called internal differentiation, which basically means that the larger planets are differentiated based upon density. And that's true with all the planets. The terrestrial planets like Earth, the more dense elements are located in the core. And if you look at the reference table on page 11, you'll notice that we already talked about the internal differentiation of the core versus the mantle versus the crust. It's all separated based upon density. And the same is true with the other planets. And the same is true with, the big Jovian large gas giants. They have a core, which they suppose is either liquid or solid. They're not quite sure. Some people believe that Jupiter is actually a liquid hydrogen core, which is kind of interesting, but it's more dense in the center than it is on the outside. And so the idea that density is what differentiates the internal structure of all the planets is pretty withheld by all the scientific community. This kind of shows that, if we have a little bit more of a liquid beginning, we can have elements moving towards the center. So as they were starting to form, the more dense material is sinking down to the bottom here into the core, and the less dense material is rising to the surface. And now we have our nice differentiated internal structure of the Earth, as you can see in this diagram here. It's a good thing to know, not often asked about, but I just figured I'd throw that out there. Now, you guys know the solar system is made up of 8 planets with a lot of other dwarf planets, including Pluto. And there's, quite a few comets and asteroids that are sailing through our solar system as well. So we'll start with Mercury. Mercury has an 88-day orbit. So in other words, 1 year on Mercury is 88 days, Earth days. So it spins or revolves around the Earth pretty quickly. Interesting thing about Mercury, it's really close to the sun, and therefore the temperature on the surface rises to about 801 Fahrenheit, which is pretty ridiculously hot during the day. And it's enough to melt lead on the surface. So it's super hot. It has no atmosphere whatsoever, nothing to block anything from the sun. So it just heats up really, really hot during the day. And then when it rotates and spins and the other side is dark, it gets super cold at night, negative 279 degrees Fahrenheit at night. Now, interesting thing about that is the fact that 1 day on Mercury is actually 59 days. So you would have 28.5 days of it being super hot, and then 28.5 days of it being super cold. So it's just kind of a crazy environment. The surface is kind of like the moon. It's covered in craters because there's no atmosphere to kind of burn up those asteroids that impact it. It's going to get covered in craters just like the moon. Okay. So that's Mercury in a nutshell. You can learn more about it if you want to research it. That's a surface of Mercury. You can see it's obviously got a lot of craters on it. And we can observe this pretty easily, even though it's pretty small. Venus, interesting thing. Venus is about the same size as Earth. So it's got an equatorial diameter that's pretty similar to the Earth. Totally different environment on the surface of Venus. It's got a really thick atmosphere that's mostly carbon dioxide. It does have sulfuric acid in the atmosphere, so it actually rains sulfuric acid on the surface. A lot of carbon dioxide, and if you remember, carbon dioxide is a greenhouse gas. That means that it's going to trap heat. So it's closer to the sun, so it's going to get hotter, but also it's trapping all that heat, so it keeps it at the surface. So average temperature on the surface is somewhere in the 700 degree Fahrenheit range. It can get hotter than that, depending upon time of year and so on. pretty crazy environment there on the surface. I mentioned this the other day, that the rotation rate is actually greater than the revolution rate. So in other words, it's a day is longer than a year on Venus, so it takes a longer time to rotate than it does to go around the sun, which is kind of a funky calendar if you think about it. Okay. We just were able to see Venus a few weeks ago. Now it's kind of getting in the path of the sun, so we can't see it anymore. It's going to be out during the day, so you're not going to see it anymore, but you will in a few months after this. It's a really bright object in the sky because it's close to us. Okay. So interesting stuff about Venus. Again, you can look into more detail about it. There's a good image of Venus. Earth we know about, we've been studying all year long, so I don't need to talk about it. But obviously it's the only planet to have life. And that is obviously due to the fact that we are in what's called the habitable zone. So a good distance away from the sun. We have water, obviously, which supports life as well. And we've been talking about it for a while now. Earth has a moon, which we know about, which we're going to talk about actually starting tomorrow. So we'll be talking about, the moon, and the phases of the moon. We only see one side of the moon, and we'll talk about why that is. We've been to the moon, obviously, and we're apparently going back. So that's kind of exciting. We'll talk about phases. You don't know what phases is yet, but we'll talk about that. Same is true with this one. Okay, Mars after that. Mars we've gone to, obviously. We've sent probes to, and we've got little rovers going across the surface of it right now. It has a very thin atmosphere, carbon dioxide, not enough to trap enough heat to make it warm. It's pretty cold there on the surface. It's got that rusty red color because most of the rocks on the surface are very iron oxide rich, so that gives it a nice red color. There are volcanoes on Mars. No known plate tectonics on Mars, which means that the volcanoes that form are going to get really large. And we talked about that when we talked about hotspots on the surface of Earth. Olympus Mons is the biggest volcano, at least known and observed. And it's huge. It dwarfs Mount Everest and all the other things on the surface of the Earth. Okay, so that's Mars. After that, we have the Asteroid Belt. And the Asteroid Belt is made up of a whole bunch of asteroids, which are kind of like tiny little planets. The biggest is Ceres, but they're all are much smaller than our moon. Okay, and there's a whole bunch of fragments of them that orbit around in between Mars and the orbit of Jupiter. Jupiter is huge, obviously. It's got a very large diameter, which means it has a lot of gravitational pull, which means it's going to have a lot of things orbiting it. It has, I think, about 60 moons. An interesting thing about Jupiter is that it rotates every 10 hours, so its spin is really, really fast, which is going to cause the gases on the surface of it to spin around, and you're going to have a very stormy surface of gases. One of the well-known storms here is this giant red spot, which you can look into. It's interesting because it rotates counterclockwise, and it actually has been observed for the last 360 years more. Since they've had telescopes developed, they've been noticing that red spot. So it's obviously been a long-lasting storm. I've heard that the outer part of this has wind speeds of up to 200 to 300 miles per hour. So it's like a giant hurricane. And by the way, it actually is bigger than the size of the Earth. Earth could fit inside of that giant red spot on Jupiter. So kind of crazy stuff. Saturn. Saturn has a very extensive ring system, as you guys know. That's what it's known for. Interesting thing about this ring system, you could be here. That would be like, let's say, Earth. And then over here, that would be the moon. So it's a really extensive, long ring system, quite large. But the thickness of those rings is only 1 kilometer, which is kind of crazy when you think about that. It's a really thin ring, but it's really wide. It's super cold on the surface of Saturn, but they think the core of it is quite hot. Most of the things that are in the ring are ice, chunks of ice and rock, and it's spinning at a pretty fast rate as well. There are 31 moons that also orbit around Saturn, much further out. And like I mentioned just before, it has very strong surface winds of 500 meters per second, which is obviously really fast. One really interesting fact about Saturn is that its density is 0.7 grams per cubic centimeter, which means if you were to put it into a ginormous glass of water, it would float, which is kind of cool. There's a good picture of the rings. And Uranus. Uranus is next. The cool thing about Uranus is that it is tilted on this really steep angle. Remember, our tilt is only 23.5 degrees. Its tilt is ridiculous. It's spinning in a weird angle, and I forget exactly what that angle is. They think that it was due to a collision. They collided with something else that made it tilt like that, though they don't really know. There are 27 moons that orbit around Uranus. It's got this blue-green color due to the chemical makeup. And it's made up of, it's called an ice giant because there's a lot of frozen gases there. Neptune, last planet. Neptune is very cold, obviously much further out, 59,440 Earth days to orbit around the sun, which is about 165 years, which is kind of crazy. And Neptune is actually just slightly smaller than Uranus, so it's a pretty similar size. Dwarf planets. Beyond Neptune, we have some dwarf planets in what's called the Kuiper Belt, Eris and Pluto. And Pluto obviously was demoted from being a planet to a dwarf planet. Due to its size, it has to kick other things out of its orbit, and it's surrounded by a whole bunch of other objects in its path. It's also got a orbital plane, which means it doesn't orbit in the same plane as the other planets. It's actually tilted quite a bit, so it doesn't kind of qualify according to the standards of what a planet might be, and it doesn't have enough mass to attract or to dispel all the other objects around it. It takes a very long time for Pluto to orbit the sun, 90,520 Earth days. So obviously a really long year for Pluto, and it's really far out there like we've talked about. Okay. There's a lot of information on the internet about all these planets. There's really good videos out there. And I know I just kind of went through that briefly. I'm going to give you some questions based upon your reference table to do today. But hopefully you guys at least have some interest in this, and you can look into more details on your own. Okay, so that's it.